Good morning, class. Welcome to the online classes for physics of class 12. In the last previous sessions, we were seeing the chapter that is moving charges and magnetism. And today's class, we are going to start the new chapter 5, that is magnetism and the matter. Here, we are going to see about what the magnets are, types of magnet, and their properties, and what are the works of this magnet. We all are familiar with a magnet because this is the material which is used in our daily lives also, and the playing thing which we used to play with a matter. So here this is a type of magnet where we can see, but different types of magnets you can just see in your daily life, and its use and the application is also in the wide range where we can see the different magnets and its uses. We see on doors, we see in the fridges, we see in our TVs, and there are many more applications which we can see these magnets in our daily life. So here we are going through the intro and the types of the magnets, that what are the magnets are. So before going to the intro, we know that magnet is a material that has a property to attract, right? It attracts some objects like made up of iron, cobalt, nickel, etc. So magnets are the properties of attraction. They have the property of attraction. And we also know that this magnet is also used for knowing the direction, that is south and north direction, by using the compass. So we also know that when we suspend freely these magnets, they just align themselves to the geographical north and the south direction. So these are the magnets. So these are the types of the properties which we used to see about the magnets. So we know that these magnets about from the childhood onwards, right? But this theory and the nature of these magnets were known from the last ancient times, that is before 16th century. To from that time onwards we are knowing about the magnets. So what was the story related to this magnet, and why this name came for this, that it is a magnet? So early in the 6th century, so the Greek, there was an island named as Magnesia. From there came that magnet. So what this magnet originated from, that is Magnesia, it was in the Greece. He found that the persons, shepherds, when they take their sheep for grazing, they came to know that they were not comfortable in walking. They used to wear the shoes which are made up or have some iron nails, and taking for grazing the sheep, they used to have a sticks which have a small iron nail which used to attract. So due to which they think that some arrangement is there at the land in the downward where this iron nails are going to be attracted, and they are not comfortable for walking. So this is what the under the land is there, which is a magnetic element. So they came to know that there are some material which has this magnetic property. So this attractive property was named as a magnetic property. From these, since it is found first in the magnesia, so it was named as magnetism. So after that, China was also the country which have discovered this lodestone. When he came to suspend it freely, he came to know that it shows is the geographical north and the south, because it aligns itself to the geographical north and south of the earth. Means he came to know about the leading stone. What he did in the China, when the king went for a war, he had a chariot in which he fixed a magnet, due to which it is always directed towards the south direction. So from there he named it as leading stone, that was named as lodestone. So China, Greece, from there all these ancient stories, it was clear that the magnetic property and about the magnet, it was early known. Not only now, but it was known from the 6th century onwards, that is from BC. So the magnets are the matter which have the attractive property and are in a wide range of application in our daily life. So these magnets have the attractive property, and due to these properties they have a lots of applications. Here we know that the magnets are of two types, but firstly we will see that magnets can be just defined into two types, that is natural magnet and the other one is artificial magnet. So the natural magnets are the materials which have this property of attraction with them, which are found in the nature, are said to be the natural magnet. Whereas, due to their inconvenient shapes, we came to know about the artificial magnets. But these natural magnets are not that much strong. Magnetically, they were not strong. They just have the attractive property, so they were said to be the magnetic substance, that is natural magnets. But by making to acquire the properties of the magnet, some instruments are used to be made as the magnets, and these properties of acquiring the magnet's property is said to be the artificial magnets. So such magnets which are just used to be made by acquiring the property of magnet, like pieces of iron and other magnetic materials which can be made as magnet, are said to be the artificial magnet. Since the magnetic materials that are the natural magnets have some inconvenient sizes and shape to use, so the artificial came into use. And these have convenient shape and the size. And they are in the various forms which can be formed between us so that we can use it easily. We can also say that the natural magnets are inconvenient in size and shape, as well as they have weaker in the magnetically, or we can say that they are not that much strong as the artificial. But since we are making the artificial magnets, so the artificial magnets are more stronger than that comparing to the natural magnets. So if we talk about the types of the magnets, then there are bar magnet, magnetic needle, horseshoe magnet and ball-ended magnet. So these are the shapes, are related to their shapes they were named as. That bar magnet, that is the rectangular or the circular cross section they will be having, that is the area section will be in the form of a rectangular. If you talk about the magnetic needle, then they are pivoted at its center so that it is free to rotate in the horizontal plane. Similarly, horseshoe magnet, it has the shape of a horseshoe. Similarly, we have seen in the first figure also, that is the horseshoe magnet itself. So they are just shaped in the horseshoe. And the next one, there's ball-ended magnet, there's ball of a circular area are in their two spherical ends. The type of the magnets. Now we were talking about the properties of the magnets. So what are the properties of magnet? We are reading it from the childhood onwards, that is from the primary classes itself. That the magnetic have the property to attract and repel. So this property is said to be the attractive property. That is, there are some materials, that is the magnetic materials, have the property to attract towards the magnet, and that materials are said to be the magnetic materials, such as iron, cobalt, nickel, etc. When a magnet is near the iron fillings or near iron objects or any other magnetic materials, the ends of the magnet shows the greatest attraction. That is, the materials are attracted towards the magnet, and these ends where the maximum attraction is being seen, that are said to be the poles of the magnet. And we know that there are the two poles of the magnets which are named as, one is north pole and the other one is south pole, that is N and the S. So from where the maximum attractive property can be seen at the ends of the magnet, then it is said to be the poles of the magnet. And how many poles are there in every magnet? There are two poles that are named as north and the south poles. That is at the ends of the magnet. And next property of the magnet, that is the directive property. So whenever the magnet is freely suspended, then it is always aligned towards the geographical north and the south. Why? Because Earth itself behaves as a magnet. Okay. So by seeing that, we can say that they will always show the direction towards the south and the north. Now the next property, that is like poles repel and the unlike poles attract each other. That is, if we bring the two magnets having the different poles and they try to attract each other, that they will be moving towards each other. And if we bring the two poles that of different strength are to be bring near the magnet, then they attract each other. If just north and south will come towards each other, then they will attract. And if north and the north poles are allowed to come towards each other, then it is said to be repelling. Similarly, magnetic poles exist in pairs. What does it mean? That if the two poles of magnet, if we break it, it doesn't mean that the north and south pole will be divided. But if we divide that or we just break that magnets, then the different two parts will have their own magnets poles, that is north and the south poles. That is, if we will break again it into some pieces, and then also they will be having their own poles. So they have some dipoles which they will exist everywhere. So we can break it into 2 to 3 poles, then also they will have their own poles. So the next property, that is magnetic induction. So you can say that the magnet induces magnetism in a magnetic substance, right? Because whenever we bring a iron nail towards it, it just try to attract towards it. This is the magnetic induction on that object. And if we keep that iron nail towards the magnet in the last time, then it just behaves as a magnet, right? So this phenomenon is called the magnetic induction, that is on inducing a magnetism in the magnetic substance. When a north pole of a powerful magnet is placed close to the soft iron bar, the closer end of the bar becomes south pole and the farther end will become north pole. So the magnet attracts the iron bar and thus the induction produces over here. So these are the properties of the magnet. So you can see here also, that is the magnets just try to attract the properties, that is the magnetic substance which have the magnetic property. Similarly, they have the two poles that are named as the north and the south pole, and we know the property that the similar poles, that is the same poles, repel each other and the different poles try to attract each other. Okay, so there are some important definitions of the words which we are going to see. First thing, that the magnetic field, we know and we have seen in the moving charges and magnetism also, that the magnetic field is the space near or around the magnet which or the object with which it is influenced by the magnet. That is, to the different or to the distance range, then iron nail does not attract the magnet. But when we take it near to the magnet, it is the range from where it will start attracting, and from that range we can say that it is experiencing the influence of the magnet. So the space around the magnet from where the object can be influenced by the magnetic effect, that range is said to be the magnetic field. And what is uniform magnetic field? That is the reason which is to be uniform. It has same magnitude and direction at all the points of that region. Because uniform means it should have all the equal magnitude. Similarly, magnetic field, if it is in a region, is said to be uniform if it's have the same direction and have the same magnitude. Similarly, you can see here the three figures that is represented for the uniform magnetic field. So first one, that is a magnetic field parallel lines, that is if we're taking a plane of a paper, then if it is acting parallel to that of the plane of the paper, it is said to be the uniform magnetic field, but it is shown by the parallel lines. Second one, it is shown with the help of the dot, that is the magnetic field acting perpendicular to the plane of the paper, but it is directed outwards. So it is represented by the dots. And when it is acting perpendicular to the plane of the paper but directed inward direction, so it will be shown with the help of the cross sign. Similarly, what is the magnetic poles? We know that the magnets have the two different poles, that is north and the south. It is the ends where the magnetic strength is maximum. Similarly, the regions of apparently magnetic strength in a magnet where the magnetic attraction is maximum, here itself it will be the poles of the magnet. So the line which is passing through the poles of these magnets is said to be the magnetic axis. And if we take a line passing through that is normal or the perpendicular to the right angles at the magnetic axis, is called the magnetic equator. Like the equator of the earth, it passes through the center from the 90 degrees. Similarly, the magnetic equator is also a line passing through the center of the magnet, making perpendicularly bisected. Similarly, what is magnetic length? That is the distance between the two poles of the magnet is said to be the magnetic length. That is, can be seen as the distance between the north and the south pole of the magnet. And we have seen the different law of forces, but here the Coulombs law of forces for the magnetic poles, because we know that if we take a two poles or the different charges, then it is stated by the Coulombs law, and we used this in the electrostatic chapter also, and we have seen it in the moving charges and the magnetism also. So what this Coulombs law of the magnetic force means, that this Coulombs law, we always say that whenever the force of attraction or repulsion are there between the two poles or the charges, it is directly proportional to that of the product of the two poles or the charges and inversely proportional to the square of the distance between them. So if we take that the pole strengths of the magnet at the ends be m1 and m2, then the distance between them be r, we can write that the force is directly proportional to the product of the charges and charge pole strength, that is m1 and m2 upon r square. So it is given by force is directly proportional to qm1 into qm2 upon r square, that is the pole strength. Here, by taking out the proportional sign, we will be getting a constant, and this constant is given by mu naught upon 4 pi, which we have learned in the previous chapter also. What that mu naught upon 4 pi was, that is permeability of the free space. And we know that this mu naught upon 4 pi was equals to that of 10 to the power minus 7. But it will be in the unit of the force itself, that is Newton. So this is what the Coulombs law of magnetic force was. It is similar to that of the electrostatic force, but here instead of charges we are using the pole strength. Now the magnetic dipole and the dipole moment. This dipole means the two different equal and the opposite charges, right? In the last electrostatic chapter, or maybe in the electric field chapter, you may have seen the two dipoles, okay, and that also the charges were there. It is one if it is q, then the other should be minus q. That is the two different charges. If they are kept at some distance between them, then they are said to be the magnetic dipole. And similarly, this is the magnetic dipole, that is arrangement of the two equal or the opposite magnetic poles which are separated by some distance are said to be the magnetic dipole. So every magnet has a dipole because they have the property of having the two different poles, that is north and the south pole. So what is magnetic dipole moment? The moment of the magnet is defined as the product of the pole strength, that is what is the strength of either of the poles, because we know that the strengths were taken the same, only the magnitude was same but the opposite of direction. So the directions were different but magnitudes are of the same. So here either of the pole strength, product of either of the pole strength and the distance between them is given by the magnetic moment, and this magnetic dipole moment is given by small m, that is equals to m into 12. So this is what the magnetic dipole moment. So what it is given by, that SI unit of magnetic dipole moment is charge. For that it is given as ampere, and for this 2L, that is meter. So ampere meter is for the charge pole strength, and for the 2L it is given as meter. So together we can write ampere meter square. So this is what the unit for the pole strength, or we can say that the magnetic dipole moment. So these were the three formulas which we have seen here. Regarding this, you can see these two numericals also. That is the two magnetic poles, one which is 4 times the stronger than the other. So if one is the Q, then the other should be 4Qm. Exerts a force of 5 gram for 5 gram F on each other when it is placed. It is 5 Gauss, okay, sorry, it is 5 Gauss, which is given as minus gram. It is, that is gram. It is given by 10 to the power minus 3 if it is multiplied or changed into the kg. So it can be changed into the force, that is force is equals to mass into acceleration. From there it came. So together if we write it as, then it can become 5 into 10 to the power minus 3 into 9.8, that is for G. So now it is here that when placed at a distance of 10 centimeters, so between them the distance is given by L, that is 10 centimeter or 0.1 meter. So find the strength of each pole. We have to find out the strength of the each pole. So Qm is given was 1 as Qm, and the other one was 4 times stronger than the other. It is given as 4Qm. So for the value of force, we can write it as 5 into 10 to the power 3. For gram it is converted into kg, and the force friction's value is given as 9.8 Newton. So for putting these values, and mu naught upon 4 pi as 10 to the power minus 7, one charge is 4 times the other charge, which is taken as 1 as 4 Qm, and for radius it is 0.1 meter at its whole square. So on solving this, we have got that Qm is equals to ampere meter. So this Am is used for the pole strength, and if we take as a dipole moment, then again L will multiply to it, so it will become ampere meter square. So the next question, two similar magnetic poles having the pole strength, that is together there are two different poles, that is from the first pole and the second pole, and the ratio 1 is to 2, and they are kept at the distance 1 meter from each other. Find the point where the unit pole experiences no net force but due to the two poles. And where is the point where there will be no force? That is in the balanced position or in the equilibrium point. So there the two forces acting should be of the same magnitude but in the different directions. So mu naught upon 4 pi q, and let the distance between them be x. So what it will be, that one pole will be having the x, other will be 1 minus x, because it is together, it is 1 centimeter. 1 meter, sorry, it is kept at a distance of 1 meter, so it is taken as 1 meter, and from other distance we don't know, so we are taking it as x. So other one will be 1 minus x. On putting this value, that one pole strength be 2qm and the other one will be qm, and putting the distances as one as x and the other one be 1 minus x. So putting these values, we got an equation that x is equals to 1 upon 1 plus root 2. So on putting the values of root 2 and together on adding and dividing it, we get 0.414 meter for the point where we will be finding or a unit pole experiences more net force due to the two poles. So from here you have seen that what is the magnet, dipole moment, what are the poles of the magnets, and what are the properties of the magnet. And we have seen its applications, where it have the wide range of the applications. So in the next class we will be seeing a few topics more about this magnet and the magnetism material. Thank you, class.